Hey folks, welcome to this channel and welcome to this video. I am Saptarshi Mukherjee. I am a software engineer 3 at Google and I have been a computer programmer for a good amount of time. So in this particular session, I'll be focusing on this topic, minimization DP, which is very common in this subject of DP. So it's very common across contests, across your DSA exercises. Let's see what this is. This is a kind of DP where we need to basically find what is the minimum number of moves or number of steps or cost. What is that minimum kind of thing to get to a certain thing, get to a certain defined thing, get to a certain result or a certain value. That is what we express, and this is the DP state that we call it. This is DPI. We say for DPI basically represents what is the minimum number of moves or steps or cost to get that value. And now the catch over here is that first of all, this happens in moves or steps, and what happens, what is basically defined, what is going to be the approach for I. Similar approach exists for I minus 1, I minus 2 or lesser values. And somehow if I know those values, if I know the answer for I minus 1, I minus 2, I minus 3, if I know those values and lesser values, then calculating this becomes easy. That is the fundamental requirement of DP. That if I somehow know that based on a certain parameter, the lower values of those parameters, the answers for the lower values of those parameters can actually help me calculate the actual answer very easily, then I actually see this as a DP problem. Which means that for lesser values of I, if I know the answers and using that, if I can find out the answer for I easily, then that becomes the approach. That let's calculate for lower values of I and use those values to calculate the ith value. That is the principal thing about DP that is common across all DP problems. So yeah, we will see how it is applicable for these kind of problems and how these problems are solved. And for this, we will look at a CSES problem, which is minimizing coins. So let us see what this problem says. It says, consider a money system which has n coins and each coin has a positive integer value. It's like the coins that we use, the 5 rupee coins, the 2 rupee coins, the other coins, etc., whatever we use. So basically each coin has some value. Your task is to produce a sum of money x using the available coins in such a way that the number of coins is minimal. Which means you have to minimize the number of coins to pay to get a sum of money x. It's something like you are paying x and you want to pay that amount using coins only, using these given coins only, the coins of given denominations, and you should ensure that the number of coins is as minimum as possible. That is, if you tell me, okay, 4 coins are needed, I should not be able to find out a way to pay using 3 coins. The minimum number of coins. If you are using the same coin multiple times, you should count it multiple times. For example, over here, you have 3 coins, 1, 5 and 7. So here the desired sum is 11. You have to reach the target 11. Now, there are multiple ways. So let's see. This is the objective, that you have to find the minimum number of coins to get a sum of money x. You have these coins and this is your target. Now, if we look at this, this is one way, 5 plus 5 plus 1. 5 plus 5 plus 1 gives us 11, which means I'll use 2 5 denomination coins and 1 denomination coin. So then I get basically I'll be able to pay using 3 coins. I can use only these denominations. I can't use any other like 6 or 7 or 2 or anything like that. 7 is allowed, yeah. So 551, 155, these are different possibilities. I can pay using 155 also. It's the same thing but in different order. For some problems, I mean, you might have to consider different orders. For some problems, the order doesn't matter, like this problem. Here, in what order you are, actually arranging the coins doesn't matter. What coins you are taking in total, that matters. So both of these are actually 3 coins. If I look at some other example, like 17111, this will give the same sum of 11 using 5 coins. Similarly, I can say, okay, I'll not use 7, I'll use 5, but only 1 5. Then I'll basically end up over here 6 ones and then 1 5. then I'll be able to pay in 7 coins. So out of this, if you see, which is the best? According to the question, in the question, I basically want to minimize the number of coins. What we are minimizing is a very important thing. So here we are minimizing number of coins. Over here, if we see, the minimum number of coins is 3, and hence 3 becomes our answer. So we will be given an array which contains the different denominations, and then using them we have to say what is the minimum number of coins we have to use to reach a certain sum. A standard DP problem, a standard minimization DP problem, and now we will see how to solve it. But before I go how to solve it, there is a very related concept or a very related problem that can be actually derived over here, that can be discussed over here, which is what is the number of ways to get this. This is one way. Like this is basically we are focusing on only one way. That is what is the minimum number of coins. I can ask you what is the maximum number of coins to get it. The other kind of problem that you get over here is what is the total number of ways. What is the total number of ways? So in that case, we have to count all of these. We have to count all of these. This particular count is going to appear over here. And this is related to a problem that we discussed in our previous class, which is dice combinations. We sort of did a similar thing. You can look there. I've pasted the link above. You can look at that problem as to how we solved that. We will solve more of those problems in coming sessions. But now coming back, our current problem is not about total number of ways. It's about a particular way. So we will not try to accumulate how many possible ways are there. We will try to minimize. And now let's see how we can minimize it. Okay. So for 11, x equal to 11, we have to solve this problem. What is the problem? The minimum coins to get, the minimum number of coins to get x, which is 11. Right. Now, what do we know? That in case of 11, it will be something plus something plus something. In this way it will occur, right? The sum of values of different coins. Now, the first coin that I choose over there can be one of the 3 coins that I am allowed to take, right? So I'm allowed to take these 3 coins, 1, 5 and 7. So these are the 3 possibilities I have. For my first coin that I choose, I have these 3 possibilities, 1, 5 or 7. Now, I basically focus on these 3 possibilities. If I take 1, then what happens? If I take 1, that means the remaining part is 10. That 10 I have to fill using the remaining coins. If I take 5, then I have 6 remaining which I have to fill using different coins. And if I take 7, then I have to fill using other coins. I have to fill 4. I have to fill the value of 4 using other coins. Now, if I look at what will my answer look like, or in these different cases, how should I visualize my answer? When I, let's say, choose this, let's say I will choose a 5, and then the remaining 6 I can do in many ways. I can take 1, 5 or 5, 1 or 1, 1, 1, 1, 1, 1 or 1 and then 5 or, we can do a lot of things. Now the thing is, if I take 5, this 6 can be taken in many ways. Which way are we interested in? There are multiple ways of filling this 6. Which way are we interested in? The minimum number of ways, right? So what we say is, hey, 11, for 11, these are your choices. Focus on a certain choice. Let's say 5. Let's say we choose 5. We will consider other cases as well, the top and the bottom. But for now, let's say we are choosing 5. Then we can say, okay, for 5, 1 coin gets consumed in the 5. Right? 1 coin goes for this 5 coin. This 5 value coin gets counted as 1 coin. And then this 6, whatever is the minimum value for this 6, whatever is the minimum number of coins to get 6, I can add 1 to it and I can say, okay, this is a possibility. Right? I can say, okay, 5 I am treating as 1 coin. And then the remaining 6, I will basically find out the answer for it. That what is the minimum number of coins to get 6. So, in that way, I can say, okay, the minimum number of coins to get 6, I know that 5 plus 1 is the minimum. So 2 coins are at least needed to get 6. So I can say, okay, then the answer is 1 plus 6 equal to, sorry, for this you need 2 coins, so 1 plus 2 equal to 3. Similarly, on top, if you rather would have chosen 1, then 10, in how many ways can you get 10? You know you can get 10 in 2 ways. Sorry, using 2 coins you can get 10, which is 5, 5. That is the minimum. So again you can say, okay, 1 goes for this one plus 10. I mean for 10, you need 2 coins. So 1 plus 2 again, in 3 ways you can get. If you choose your first number as 1, first coin as 1, then also in 3 ways it is possible. Similarly, for this 7, if I choose my first coin as 7, then what comes? The remaining part is 4. For 4, I have only one possibility. 1, 1, 1, 1. 1 plus 1 plus 1 plus 1. Which means first coin is of 5 is of 7, and then 4 coins for 4, 4 1 value coins, which gives me in total 1 plus 4 equals to 5. So for each possibility, these are my 3 possibilities. In these 3 possibilities, look at this. I have 3 other things to see. For those 3 things, if I know what are the minimum coins to get those individual things. So I'm basically asking, hey, for 11, I can make some choice which will either lead to a remainder of 10 or 6 or 4. Then if 10 gets done faster, I should go to that category. If 6 gets done faster, I should go to that category. If 4 gets done faster, I should go to that category. And this is the way to actually think about. So it's basically like this, that let's say 10 is possible in X ways, Y is possible, or sorry, 10 is, for 10 the minimum number of coins required is X, for 6 it is Y, for 4 it is Z. So we can basically say, then for 11 the minimum cost is the min of 1 plus X, because this one needs only one coin, 1 plus Y, because this 5 also needs only one coin, and this one will need Y coins, and 1 plus Z. These are your 3 possibilities. You can also write this as 1 plus the minimum of X, Y, Z, which is nothing but, so here we are basically calculating the answer for 11. The answer for 11 is basically 1 plus the answer of, the minimum of the answer of 10, comma the answer of 6, comma the answer of 4. And in DP formulation, we write the same thing as DP of 11 is equal to 1 plus min DP of 10, DP of 6, DP of 4. Which means if I know the minimum coins to get smaller values, I can easily get the minimum coins to get the greatest value for which the answer has been asked to us, for which we have to actually return the answer. So if we know the answer for greater values, finding for the lesser values, finding for the greatest value, the actual value, is a simple minimization, is a simple min kind of problem. Take the values, do the minimum, get the result. Make sense? Right. So now we can express this as that, okay, we have an array A given to us, ARR, some array A given to us, N. Let me name this as the coins you have. Let's say there are such N coins. Then our answer, the DP of any I, is basically the minimum of, and we can add 1 before it, 1 plus the minimum of or we can add this one here as well. Minimum for j goes from 0 to n minus 1. We can say it's 1 plus coins of, sorry, 1 plus dp of I minus coins of j. So what is this? We are basically saying take coin j and then go to I minus coins j. That's exactly what we were doing over here. Go to 11 minus 1, that is 10. 11 minus 1. So if we see the same thing here, so here the coins array will look like this: 1, 5, 7. And then we are basically saying, okay, dp of 11 is equal to the minimum of 1 plus dp of 11 minus coins of 0, that is 1, this 1. So 11 minus 1, 1 plus dp of 11 minus 5, 1 plus dp of 11 minus 7. And then you can take the 1 outside. So in this way you can solve this problem, which means now if we look at this, dp11 or the answer for 11 depends on the answer for 10, 6 and 4. For 10 also, you don't have any measure, any magical thing to find out the number of coins very easily. For 10 also you should do the same kind of thing. Using 1, 5 and 7, what is the number of coins? You have to find the answer for 10 as well. For 10 also you have to come down. For 10 also you have a similar dependency. So if I look at it in that terms, that okay, 11 says I have 3 possibilities. 11 says that I have 3 possibilities: 1, 5 and 7. If you take the path of 1, you remain with 10. Take the path of 5, you remain with 6. Take the path of 7, you remain with 4. For 10, do the same thing: 1, 5, 7. So basically if you come down through 1, you remain with 9. Through 5, you come down with 5. Through 7, you come down with 3. For 9 again, the process will continue. For 5, 1, 5. For 7, this is not applicable. We should not subtract 7. 7 cannot be used when we are basically looking at 5. So that is one invalid case. We have to be careful. We have to have this kind of a condition that the coins j, this is something we can actually incorporate in our program, that our coins j has to be less than equal to I. If some particular coin is greater, you cannot take that. Take the other coins. That is the idea. So okay, 7 I'll not take. If I take 1, I will end up with 4. If I take 5, I'll end up with 0. For 3, I can only take 1. So I'll end up with 2. For 2 again, I can only take 1. For 1, I can only take 1, 0. 0 is that case for which we know okay, nothing else is needed. For 0, I know that okay, for 0, no coin is needed. 0 coins are needed. 4 will go down. I know 4 will go down. And then for 4, the answer basically will come out to be 4. We need 4 coins. For 7, it is not possible. So this 5 will say, okay, if I go through the 1 root, through the root of 1, I get 4 plus 1, 1 plus 4. This plus 1 I have to do with each of them. So 1 plus 4. If I go through this 5, I'll get 1 plus 0. So it's minimum of 1 plus 4 and 1 plus 0, which is 1 plus 0. That is the best we get. So I'll take 1 plus 0, which is 1. So for 5, I need 1 plus dp of 0, which is 1 plus 0, that is 1. For 3, similarly, I will say, okay, for 1, it is 1 plus 1, that is 1. For 2, again, it is 1 plus its child's value, that is 1 plus 1, 1. Sorry, 1 plus 1, 2. For 3, again, it's 1 plus 2, that is 3. And for 10, for 10, it will again be 1 plus minimum of, for this 9, you have a possibility of 5 plus 1 plus 1 plus 1 plus 1. So over there you have a possibility of 5 coins. Like this 9 you can complete in 5 coins. So it is 5 plus, okay, so this is 5. 5 can complete in one set, this particular 5. And the 3 can complete in 3 coins. So you have 3. So minimum of 5, 1, 3, that is 1 plus 1, 2. which means that 10 can be completed in 2 sets. We know that DP of 10 is 2. Similarly, 6 can be completed. At the minimum, it needs 2 coins only, 1 and 5. 4 needs 4 coins. So for this, again, the same minimization thing comes, 1 plus minimum of all its children. DP of 11 minus 1, the above expression. So basically over here you have 2, over here 2, over here 4. So let's do that. 1 plus min of 2, 2, 4. That gives us 1 plus 2, that is 3. So we notice the same thing over here as well. If we take 1 or 5, we are able to get 3 coins. If we take 7, we will end up with 5 coins. That is the exact thing that we are observing over here. 3, 3, 5. And here, 3, 3, 5. Yeah, so from this diagram, from this tree diagram, we understand that if I have to calculate for x, I can calculate it from the subproblems. So these are my subproblems. Whatever things you have over here, these are my subproblems. Based on that, I can calculate the main problem. Which means from the subproblems, I get first of all the first thing, that is optimal substructure. For this detail, what is optimal substructure and all these things, go to this video that I've linked above. Here you will actually see I've actually described these things in detail, that what is a optimal substructure and what are other things in DP concepts. So yeah, optimal substructure, and you'll also see some common things. Some common things will come, like when you come down for 6, when you come down, let's say 6 minus 1, 5, then what you see is this 5 and this 5 are common. Which means if you calculate once for 5, you should not again calculate for 5. Similarly, this 4 and that 4 are common. If you are calculating for this 4, you again should not come down and calculate for this 4. This classifies it as a DP problem. These two things. That it has an optimal substructure, problems depending on subproblems, and it has overlapping subproblems. Overlapping subproblems. These are the two pillars which you have to abide by in DP. Optimal substructure tells you how it is related to subproblems. The moment you have that clarity that from a problem, what are my subproblems, you can immediately adopt the recursion strategy. That I start from the top, you are at the top, you start from there and you go deep down as and when you need. So you can basically start in this way. You can initially have, so that is one approach, basically going top down. You start from the top and you keep going towards the bottom. That is known as the memoization strategy. The other is the tabulation strategy, which we'll discuss right after this. So one is, let's say we will define a DP state, DP, which I will fill. This is a DP array of, you can say, whatever x is given, x plus 1. And then you can say, okay, DP, and you can fill it with all the values with a maximum number, because you are minimizing, so start with the maximum possible value, like infinity. Fill with infinity or int max. There is only one exception. For 0, you know the answer. For 0, the answer is 0. You don't need anything. Now you start the process. You can say, okay, now calculate the DP with the coins array. This DP is basically this particular array we are passing for the memoization. Do the recursion inside this calculate. And which one shall we calculate? We'll calculate for x. And I think that's what we need. We'll call this. This is our main function. We will call this. And it will look something like this. We'll have a function to calculate. And we will say, okay, int DP and something like int coins. Instead of int, you can actually take long if the question deserves that. If the question needs that, you can take. But over here, it looks it doesn't need that. 10 to the power 6 into, I mean, 10 to the power 6 is the maximum, so you don't need actually. So in DP, int coins and int I. Now, whenever you're doing recursion, the first thing is assume that your subproblems are solved. Solve it based on the solutions of the subproblems. So what can you do? You can basically call a loop over all the coins. So you can use some j. J basically goes from 0 to n minus 1. N is basically the length of the coins array. You can take that as an input. And then you will say that, okay, calculate. You can actually ignore calculating. That if this jth value, if this coins j is less than equal to the I, then only there is merit in calculating it. Then only do this. Um, can then do yeah. You can then do something like this. dp of I is equal to, or you can actually calculate this dp separately. No, this is fine, I think. dp of I is equal to the minimum of the current value of dpi and 1 plus calculate dp coins and I minus coins j. We know this I minus coins j will be non-negative. So there you go. This is the main loop where the dp value gets calculated, and we started with the maximum value, which means that always this value will be lesser than the initial value, so we'll get that as the minimum. I think I missed one bracket. Let me put that over here. Yeah. Okay. Now the next part is, this is how I calculated the dp. Now let's look at this. This is my recursive case where if I know the answers to the subproblems, I have my total answer. I'm doing it for all possible j if those j values are lesser than my current I that I'm looking for. Okay, now the thing is, in which cases will this not work? For 0 or things less than that, this will not work. For let's say in coins, the lowest value is 3. Then for 1 and 2 also, I should have something like, I mean, I can have something like int max. So it's fine to keep that as int max. Int max basically says that it is not possible yet. So let's say for 1 or 2 or other values, let's say it's not possible at all. It is fine to keep it as int max. It will not enter this loop. So it is fine to keep that as int max. That is basically the way of visualizing what are my corner cases. And it is fine to keep as int max. Anywhere if you have to say, okay, what is the minimum number of ways? If there are no ways, then return -1. You can read that, you can say, okay, if it is int max, then return -1, something like that. You can do that. But up to here, it is fine, recursive case wise fine. In what cases will this not work? It should not go deep into the subproblems. You should have a stop somewhere, you should have a check somewhere that, okay, below this, don't go. Like over here, don't go below this 0. If you keep on going below this 0, you will keep on going to -1, -2, and so on. Don't go below this 0. And for 0, you should also not return int max. I mean, over here we have added this check, so it will not go to -1, etc. But you should not also end up with int max. For 0, you should basically have 0 only. That's already over here. So in that case, you can directly return. So you can actually do this, that if, so this one actually doesn't need a base case because the base case are already filled up over here. But one thing is needed, that if the DP value is filled, then don't fill again. That is the memoization strategy. So if the DP value is filled, how to know it is filled? If DPI is less than int max, that is the initial value that you filled with, and 0 also falls over there. So this means you have to return. You return DPI. So DPI, the moment you call this with something lesser, like this, let's call it as K, it will look at whether DPK is there or not. If DPK is not there, then fine. It will calculate and return, otherwise it will directly return. So that is the thing. This is the memoization strategy, or what we sometimes call as the table lookup strategy. Table lookup strategy. So in this case, you can say this is your base case, or you can basically also make this observation: we are adding this so that it unnecessarily does not go to the negative numbers. So yes, you should go to your subproblems, but you should have some check when you shouldn't go. Over here, this and this are those conditions where it is not going. So anyway, we are following the recursion and the the base case and basically the memoization strategy that we discussed in the common class that we took on TP. You can actually find that in the in my videos. I had that common lecture on TP. Yeah. Okay. And I've added in the description as well. Fine. So this is the memoization strategy. What is the time complexity? If I have to analyze the time complexity, this will basically call the numbers like it will call each number, it will go deep into each number exactly once. So for each number, this part will happen exactly once. So you can say that part is going to be n into x plus the other things like how many times a particular value will be visited, how many times this particular thing will be run. That is slightly tricky to actually visualize. You can think it in this way that okay, I have a certain thing like I. How many times this I will be called? Think how many people will call this. This will be called by basically either by doing something like ARR or coins. We have coins. By spending the first coin, somebody can call this. By spending the second coin, somebody can call this, and so on. So basically, their parents will call them only once, and which parents will call them? I plus coin 0, I plus coin 0 will call them exactly once by spending coin 0 initially. I plus coins 1 will call them exactly once. Why exactly once? Because I plus coins 1 will get, will be calculated thoroughly only once. Then it will be reused everywhere. So they'll call only once. Dot dot dot. So dot dot dot, which means that each I each I is called at most n times by the n children. So over here, if we see how many i's are there, number of i's are x, and how many times they can be called, each one can be called maximum n times. So that is it. Or you can say x plus 1. Instead of x, you can say x plus 1. Ultimately, it turns out to be the same thing, big O of n into x. So how many times this particular thing runs, that is n into x, and how many times this particular thing is basically encountered, how many times a particular I is called, that is important for this. How many times a particular I is called? N times. How many i's are there? X plus 1. So again, x into n, something like that comes. So ultimately, you get this as the final thing, big O n plus n into x time complexity. What is the space complexity? Here we are using just this DP thing and the recursion thing. So big O n space complexity over here, big O n for the DP array in your heap space, which is rather easier to handle, and big O n in function memory stack, because it basically keeps on calling. So if it calls using 1 or even using 2, n will call n minus 2, n minus 2 will call n minus x, you can say x will call x minus 2, x minus 2 will call x minus 4, and so on up to 0, which means x by 2 steps are there. So yes, sorry, it will be x instead of n, it will be x. all of these, because we are having, I mean, whatever is the size of the DP. So it's X for DP and X for the memory stack. And for stack, we know this basically will leave some effect on your time complexity as well. So that is the reason we discussed in our last class that what is memoization versus tabulation. We had in that particular lecture, I had discussed that in detail. That memoization and tabulation, you can look at the topic. I had that separate video on memoization and tabulation. I pasted in the description that particular link. That memoization is good when you don't know exactly in what order you have to iterate, and when you don't have to iterate through everything. I actually showed examples of when memoization is good. Tabulation is good in most other ways. If you know in what order you have to visit, in this case, you need to know the subproblems before the problem. You know that the subproblems have lesser I than the actual problem. So if you go in increasing order of I, then you have the guarantee that when I'm reaching a certain I, the previous I's are also calculated. If you say I'll calculate for lesser values of I and then for the greater values, you have that guarantee that when I reach the greatest value of I, when I reach a certain value of I, the subproblems that are the lesser values are already there. So it's basically something like this. If I take that particular example once again, 157 and x equal to 11. And we can also take x equal to 12 to see what happens. I mean, we know the answer will be 2, but okay, let's take x equal to 11. I've drawn more. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, for 0, we know it is 0. For the others, we don't know. Let's say initially they are all infinity. For 1, I will say, okay, I can use 1, I can use 5, I can use 7. But if I use 5 and 7, I'll go outside. 1 minus 5, I mean, I'll go outside. So what will I say? Okay, go only up to 0, up to your limits. So 1 minus 1 takes you to 0. Whatever value you get, you will do plus 1, that gets stored. Similarly, for 2, you will say, okay, my predecessors are again only 1. So this needs 1 way, so I will need 1 plus 1 coin, that is 2 coins. So in this way, let me fill up few values, 3, 4. Now for 5, let us see for 5. For 5, you have two options. You can take 1 and go to the previous state, or you can take 5 and go to this state. So if you go to the previous one, that means this will need 4 coins. And for this 4 to 5, you basically need 1 more coin, which means you need 5 coins along this way. If you take it to 0, for taking 0 to 5, you basically need only 1 coin. I mean, so over here, you're basically spending the 5 value coin and you're going to 0. For 0, you need nothing. So it basically tells you, okay, for this 5, this is just a single coin. This is just 1 coin. Which means take 1 coin only. Here you need 5, I mean, here you basically need 1 coin for going to 4, and 4 needs 4 coins. So 1 plus 4, that is 5. Okay. Now for 6, I can do a similar thing. I can say you can take 1 coin, you can take 5 coins. So minimum of these 2 plus 1. Minimum of these 2 plus 1 gives you 2. Similarly, go to the next one, 7. Now you have 3 options for 7. So you can go to 7 minus 1, 7 minus 5, that is 2. Okay, you're going to 7 minus 1, 7 minus 5, that is 2, and 7 minus 7, that is 0. And what is the strategy? 1 plus the min of subproblems. This is the strategy. So see what your subproblems are. Your subproblems are from 7, it is 2, and 0. So the minimum among these 3 is 0. That minimum plus 1 gives you the answer, which is 3. Sorry, that minimum gives you the answer. The minimum is 0, 0 plus 1 gives you 1. So for 7, the answer is 1. The minimum of 0, 2, 2 is 0, 0 plus 1. So we're basically following this. 1 plus minimum of subproblems. That's what we discussed in our recurrence. It is 1 plus the minimum of xyz. Okay, Similarly for 8, we can say it goes to 7. For 8 it goes to 7, 8 minus 1, and 8 minus 5, that is 3, and 8 minus 7, that is 1. Among these three that I've marked, 1, 3 and 1, the minimum is 1. That plus 1 gives you 2. So 2 is the answer. 2 is the answer over here. For 9. For 9 again we can do the same thing. 9 minus 1, 9 minus 5, 9 minus 7. The minimum is 2. 2 plus 1 gives you 3. So you get 3. 10, you have the same thing. 10 minus 1, 10 minus 5, 10 minus 7. The minimum is 1. 1 plus 1 is 2. 11, the minimum is 11 minus 1, 11 minus 5, 11 minus 7. So the minimum is 2, 2 plus 1 is 3. In this way you are getting this answer 3. In this way you are getting this answer 3. Now if you need for 12, you can do just one step more. So basically for 12, 12 minus 1, 12 minus 5, 12 minus 7. So these three values, you take the minimum, you get 1, 1 plus 1, 2. And that is also the right answer for 12. Why? Because we need just 5 and 7 to complete 12. So in the above example, up to the previous step, we were basically looking at 11 as our destination. Here I have done one step more. So you can basically do up to x, whatever x you need, and you can return that as the answer. So this is the tabulation way. This is a very straightforward way. We are going from left to right. This is a very straightforward way. So we are taking I from 0 to x. Straightforward way. Or you can say 1 to x or whatever. We are filling the table from 0 to x. A very well defined thing. You know the order of execution. You know the order of filling. When you know the order of filling, tabulation is a good choice. If you have the space, then make such a table and fill it. Right? So what is the time complexity of this approach going to be? You are filling x boxes. You are filling x boxes. You are filling x boxes. So x multiplied by, for each box you are visiting, n different subproblems. N different coins are there to go to subproblems. You are visiting n different subproblems, so it's x into n. That is a big O notation, big O n x. So the time complexity is the same. The space complexity is also the same. It is big O x. The time and space complexity are the same, but this is totally in heap. This is totally in heap. No stack space consumed. And this looks elegant in one way. In what way? That you know in what order you are executing. This is a bottom-up way of doing things. You know that if I go in this way, I'll get the subproblems first, then the problems. It's a good way of executing. So this is the tabulation way. It's basically referred to as the bottom-up way of table filling. While this was the top-down way of filling, which we also refer to as memoization. This is the top-down strategy, which is the memoization form of DP. So let's see my code. Yeah. So for this I did not call any function, no function calls needed. That latency or the time for function calls is totally gone. If you see over here, I am taking n, x and c. C is basically my coins array. These are my inputs, and answer array is basically my DP array. I am filling the answer array with maximum value integer.max. You can fill with long.max also. Here integer is fine. Though I am having long, but integer is fine over here. Why? We have seen it will not cross 10 to the power 6. And if you add all the n values as well, the coins as well, you will get 10 to the power 8 maximum, 10 to the power 6 into 100 coins are maximum there. So you're having just two simple loops. The first one is basically going up to going from the first coin to the last, sorry, the first I to the last I, which is basically the destination, the sum of money. So it's basically saying, okay, first for amount of money, then for amount of money 2, then 3, then 4, up to X. And for each of them, I'm basically exploring all the possibilities of coins. For each coin, I'm basically saying, hey, this is the value of the coin. If the value is less than the current value, then please uh, form the minimum. So in this way, I will get 1 plus answer of I minus val. I'll get that multiple. So here, basically, I'm basically storing this in val so that this looks composed. I'm using the two val two times. You can use CJ directly. No such hard and fast rule. And at the end, this is the important thing. I am printing that if it is less than integer dot max value, then answer x, otherwise minus 1. This was given in the question. Let's see. Yes. If it is not possible to produce the desired sum, print minus 1. Sometimes it is not possible. Like let's say I have given only even valued coins, 2, 4, 6, 8. And I've asked you to form 7. How will you form 7? You cannot form 7. So then you print minus 1. So in those cases, you will actually see, I can show you some inputs maybe here. So you have one coin and you have to reach a value of 1. The sum of money is 1, but the coin is something like 10 lakhs, right? Yeah. So using one coin of 10 lakh value, you cannot get a sum of 1, right? So that's it. So basically you have to return minus 1. So you start with max value, which ensures that when you're doing this main operation, the initial value gets wiped out. This answer I, if it is a maximum, integer or maximum initially, we have a guarantee that the new value will definitely be lesser. So that will be replaced. So that is our strategy. When we are minimizing, we should start with the maximum value so that in the first step it automatically minimizes. Similarly, in the maximization problem, you should start with a minimum value, a very minimum value, so that whatever comes at the beginning, that becomes the new maximum. So this is a common strategy. We use this. At the end, you need to say, okay, if it has remained the maximum, that means you got nothing after that maximum. You got nothing. So then return minus 1. So this is a ternary operation. It's basically saying that if it is lesser, then return answer x, otherwise minus 1. A conditional statement or conditional operator. So that's it. I hope you found this session informative. What we basically discussed is a very common category in DP, minimization DP, with which you can solve a lot of problems. There are some harder variations as well, like you have a knapsack variation where you have to find maybe the minimum cost, or you have to say what is the maximum value you can obtain using some things. Those minimization, maximization problems, they don't just focus on one parameter, or the formulation does not focus on one parameter but multiple parameters. And in those cases, we have to form some 2D DP kind of approaches depending on the number of parameters. But this is the basic foundation. So if you have this flexibility that using the subproblems, I can minimize a certain value by focusing on the subproblems by using them. This is that particular DP category where you can solve problems and basically enhance your skill over there. You get a lot of problems here. This is one such problem. And a very common other kind of problem is finding number of ways. We will solve multiple problems, multiple other problems from the CSES problem set using these techniques. So yeah, solve the other problems as well. Try to solve the other problems, and then see you all in the next videos. Try to also solve using the memoization approach, and let me know if you have any doubts in the memoization or tabulation approach. Know all the approaches and then take your call which approach should be used. That's it for the day. I hope you enjoyed the session. Take care, keep coding, and see you all in the upcoming videos. Do like, subscribe, and share. If you find the videos informative, please also inform your friends, and you can watch in groups. You can basically solve questions together and then watch the editorials and these kind of problems. This is mainly focused at your, at basically bring you all to competitive programming, so that you have a foundation for solving really hard DP problems. After all these things, I'll basically come to harder DP problems outside the CSES problem set. That will probably take me a couple of months, but I'll come to them. That's it for the day. Thank you. Take care. Keep coding. Bye.